Good, how are you?
Right.
That's pretty early. Still got 10 more minutes to go. All right, it's 1 o'clock. Let's go ahead and get started. All right, good afternoon, everyone. How's everyone doing today? And have a good long weekend. Get out of the heat. It's hot this weekend. I went to I usually go to this with my wife every year. We went to Asian American Expo in Santa Ana over the weekend. It was hot. It was very, very hot. So I'm glad we made it out. We made it out alive. Okay. So the plan for today is we have just one kind of very small section of the first lecture notes that I want to finish up. And then we're going to move on to the next big section, which is called present work analysis. Okay. All right, so announcement. So your first homework is due tonight. So it's due tonight at 11:59 p.m. And so you have the option to, of course, turn that in on Canvas. And so if you do that, you just have to scan your PDF and upload that to Canvas. Or if you have it here in class, you can turn in the hard copy. I know some people prefer to have me marked directly onto their homeworks. And so if you want to do that, you can turn it in here at the end of class, and then I'll grade it. Usually for me, I try to finish all my grading a week after it's due. And so I'll have all your homework graded by next Tuesday at the latest. Okay. All right, and so I do have your homework 2 ready, and so basically after the clock strikes midnight tonight, I'm going to post homework 2, and that's going to be due next Thursday. So you have a little bit over a week to work on that. And so homework 2 is going to cover a little bit kind of the tail end of the lecture that we were covering last week, as well as present work analysis. And so keep you used to just kind of keep up the practice on a lot of these things, because I think a lot of this economic stuff is not the hardest thing in the world. It's not the most complicated, but it does require some practice, and kind of the more you practice with this stuff, the faster you get at it, and then it just kind of becomes easier and easier with that. So that's why the homework schedule for this class, I think it's a little bit, a little bit intense in the beginning, but it's mostly just to give you guys that practice, because it's going to make the stuff that we do later on in economics a lot. Okay. All right, and so are there any questions I can answer before we get started for today? Okay. All right, so let's go ahead and pick up where we left off. And so as a reminder from last week, we were talking about standard forms. Okay, so let's go back and pick up with that. Okay. All right. And so far in this class, we've gone over what I consider, 4 different forms of cash flow, right? And so, when we're planning engineering projects or when we're planning a budget, there are different forms that cash can take, throughout the course of the project, and we can classify them into 4 different types, right? And so the very first one that we went over is a present sum. Okay. Remember, we gave the present sum symbol P, right? And visually, if we look at a cash flow diagram, a present sum is just any flow of cash that's happening today, right? So remember, whenever we draw a cash flow diagram, the first node that we always draw here is node 0, and node 0 always indicates today, okay? Okay. And so P would be something like that, right? And so for a lot of engineering projects, this takes the form of some kind of initial cost. And so say you're purchasing some equipment or some material, and you use a present sum to represent the cost that you pay for those things up front. Okay. Okay. So the standard form for P is that it occurs on time 0. Okay. But you'll see in a bit we're going to use you can use P in a little bit some creative ways too. But for now, just think of P as happening today. Okay. Or you can think of P as past, right? Sometime in the past. Because the opposite of a present sum is a future sum. Okay, and we give that the symbol F. And the future sum is some kind of cash flow that happens in the future. Okay, just like that. Okay. And so basically any cash flow that does not occur, or any single lump sum cash flow that does not occur on time 0, we consider that a future sum. Okay. And when you consider future sums, the number of time periods it happens in the future is important, okay? And so if you count the number of time periods that occurs between, present day and the future, we always call that N, okay? And that's going to be important in a bit. And so, I know, it may seem fairly obvious, but I want to kind of mention it again, because once we start converting between non-standard forms, this definition for N is important, okay? Okay. Okay, so those are the 2 kind of basic cash flows. And so those are the 2 kind of single lump sums. After we went over that, we started to go over recurring types of cash flows, right? And so the first type is a uniform series. Okay, and so a uniform series is a uniform type of cash flow. Okay, and so it's a recurring cash flow that occurs over multiple time periods, but the amount is always the same. Okay? And so standard form for this is that, we assume that the uniform series starts at the first time period, not at 0. Okay. Where each of these arrows have a size of A. Okay. Okay. And so here again, the definition of N is important. Okay. But for uniform series, N here represents the number of times that the payment is going to recur or repeat. Okay. And so in this example here, I just drew just as many dots as I could fit. And so here the payment is recurring 5 times. And so here the value of N is 5. Okay. Okay. All right, and the last form of cash flow that we went over was arithmetic gradient. Where arithmetic gradient is also a recurring type of cash flow, and so it's something that's going to repeat over and over again. But instead of being a uniform amount over the time period, the arithmetic gradient is going to grow over time. And instead, this G here describes the amount that the cash flow is going to grow in each time period. Okay. This was the trickiest one. This is the one that I think trips people up the most, because the standard form for G is actually blank on time period 0 and 1. Okay. And so the standard form for G actually is, it starts on year 2. Okay. Right. I remember, so for each time period after that, the amount that the arithmetic gradient grows is going to grow by G, right? So it's going to start at G, then 2G, 3G, 4G, and so on and so forth. Okay. And the part that I think, first of all, it's tricky that the arithmetic gradient starts on 2, but the N here is also tricky as well, okay? Because you would think that, for something like this, if you're comparing it to the uniform series, you would count N as the number of arrows that you see, right? So I think a lot of people look at this and they say that, for this arithmetic gradient, N should equal to 4, okay? But you actually do count that first blank year, because that, one way that you can think of it, this is like 0G, okay? And so the N here is, basically the number of time periods that the arithmetic gradient is visual, right? Plus 1. Okay. Okay, and so for this one, just like the uniform series above it, it would be N is equal to 5. We start at 0G on time period 1, then G, then 2G, then 3G, then 4G. Okay. Okay, so why am I showing you this? And so, I think this is kind of where, the cash flow diagrams here, kind of the visual way that you can see these cash flows comes in handy, because you're going to come across problems where, you're going to get cash flows that are not in these standard forms, but you're still going to be expected to do some conversions and do some calculations, okay? And so the reason I'm showing you these standard forms is that whenever you perform a cash flow conversion, okay? And so we did a lot of that last week. And so this is either using the formulas or using the compound interest table. The assumption is that you're always converting between the standard forms of these cash flows, okay? Okay. And so this right here is kind of a really important point. So I'm going to pause. Okay. All right. And so it's an important point, but I think, maybe, I think maybe it's not so clear what it means until we actually visualize it. And so, let's say that we're doing a conversion, right? And so let's take the simple example of taking out a loan, right? And so when you take out a loan, okay, when you take out a loan, you get a very large payment up front, okay? And so, you get large amount of money, either from the bank or from your uncle who's trying to scam you, or anyone else, right? And the idea with the loan is that you're going to pay it back using recurring payments over time, okay? And so if that's what your kind of your what it looks like when you first get the loan, right? Your repayment schedule might look something like this. And so you're going to have equal payments on all future time periods, okay? Okay. For the time period, or where the amount that you're paying is A, okay? And if you remember from last time, one way that you can compute A is to perform a conversion, right? And so we're going to convert the original amount P to an A, okay? And so you can do this one or two ways. You can do this either with the formulas or with the compound interest tables. And so, just because it's a bit faster, I'm going to show how you do it with the compound interest tables. Okay, that's not the right one. Okay, and so if you're going to do this with the compound interest tables, you would need an A over P factor, right? Because you're converting to an A from a P. Okay, you would need the interest rate, and then you would need the number of periods. And so the number of periods here is N. Okay. And so this is how you would compute your either your monthly payments, yearly payments, weekly payments, whatever, right? Depends on how you interpret M. This is how you would compute your payment amounts based on your original loan amount. Okay. Remember this right here, this you would look up in the compound interest table. Okay. So that's a simple example of what I mean by when you're performing conversions. Okay. But this is a good example of what I consider a very clean conversion, right? And so what we have here is P, where P is a single lump sum at the beginning, right? And so if we look back up at our standard form for P, right? I mean, the arrow's facing the other way, but it's still occurring at the same time period, okay? And so this top cash flow diagram is what I consider standard form for P, okay? And if we look at our cash flow diagram for A, right, that's our standard form, right? So our A here is starting at year one, or time period one, and it's going all the way to the end of the cash flow diagram. Okay, so this is standard, and this is standard. Okay. Right, and so this is pretty textbook. And so we don't need to do anything special here. We just apply that one conversion factor, and we get exactly what we do. Okay. But you're going to come across cases that aren't that standard. Okay. And so let's look and see what that means. And you'll see that this is where kind of the cash flow diagrams really become really useful. Because I think up to this point, at least for homework 1, I think whenever I ask you to draw a cash flow diagram, it's kind of just a nuisance, right? So it takes up a lot of space on the paper, takes a lot of time to draw the arrows and stuff like that. And so, it's kind of, I admit at this point it's not that useful, but from here you'll see that it is very useful. Okay. Okay. So let's do an example of a non-standard cash flow type problem. Okay. Okay. And so let's say that you are in a situation where you need to borrow money over each year for a 3-year period. Okay. Right. So, because you're borrowing this money, eventually you have to pay it back plus interest. Okay. But the person that you're borrowing this money from said that, okay, you don't have to pay it back at the end of year 3. You can pay it back at the end of year 5. So 2 years, basically 2 years after you get the last payment, that's when you have to pay it back. Okay. Okay. Oh, we need the interest rate. So let's say in this case, the interest rate here is 15%. Okay. Okay, so let's go ahead and draw this out. And I'm going to draw a cash flow diagram that has up to 5 years. Okay. Okay. And so from this problem, we can see that we're borrowing $1,000 per year for the first 3 years. Okay. And so we have okay. And so that's what that's going to look like. Okay. So each year for the first 3 years, you're going to get $1,000. Okay. But then you're going to pay it back all in one lump sum at the end of year 5 as an F. Okay. And so a structure like this is you see this kind of more for startups. And so for companies that are just starting up, usually they need to borrow money not only initially but over the first few years of operations until they can really start earning money, and then they pay back all those debts kind of once the company gets some equity near the and they start doing well at the end of that. Okay. And so in this problem, what we want to do is we want to compute what that F is. Okay, and so what we have here is a recurring payment. Okay, and so we can clearly see that we have a uniform series here with an amount 1,000. Okay, so we have A is equal to 1,000 here. And this is occurring over 3 years, and so we can say that N is equal to 3. Okay. And we want to convert this to an F. All right, so the first naive thing that you can do is you can perform this conversion right here. Okay. And so we're going to perform an A to an F conversion. And so we can say is F is equal to A multiplied by F over A. Interest rate is 15%. And N here is 3. Okay. All right, and so what we can do is we can look this up in the compound interest tables. And so we're going to go to the compound interest tables for I is equal to 15%. And then we're going to look in the F over A column. And then we're going to look at row 3 because N is equal to 3 here. Okay. And what we get is a value of 3.472. Okay. Okay. And so if A is equal to 1,000, we plug that in. So we have 1,000 times 3.472. And what we get is 3,472. Okay. Okay, so that's the value that we get. The question now is that is this the F that we're looking for, or is it something else? Right? Remember, whenever we perform these cash flow conversions, we do them between standard forms. Okay. And so if you notice for this cash flow conversion right here, I set N is equal to 3. Okay. And we're converting this this uniform series into an F, right? And so what does N represent for F? N represents the amount of time in the future that this F is taking place, okay? And so that means that this F that we computed, this is an F. This is an F in year 3. Okay. So if we kind of redraw our cash flow diagram right here. Okay. Right. Okay. And so that's basically what we computed, because the uniform series only takes place over 3 years, and we're converting that directly to an F, then that F is going to appear at the end of that series, which is at year 3. Okay. Right. And so obviously this is not what we want, right? And so the F that we do want, if we look back at the original problem, the F that we do want is happening in year 5. Okay. And so what's going to happen is that if you say that you're the owner of this business, and then you try to pay this person $3,472, your lender is going to be like, wait a minute, that amount is not what I was expecting. And so you still have 2 more years for interest to accumulate on that amount that you're going to pay me at the end of year 5. Okay, so we're not quite there yet. And so we need to take this 3,472 and move this into the future for 2 more years. Okay. 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 And so the way that we can do that is we can perform a second conversion, right? And so, now that we kind of are done with this, so let me go ahead and redraw this cash flow diagram like this, okay? Just with those years. Okay. And I'm going to renumber it too, because, the beginning of the cash flow diagram is just starts with 0. Okay? So all I'm doing here is just kind of redrawing this. Cash flow diagram is a long word, and so I'm going to shorten it to CFD. If my iPad can draw D without spazzing out on me. Okay. And so I'm going to start this cash flow diagram at 0, but that's actually year 3, but we're going to pretend it's 0 just so we can use standard forms. Okay. And so what we have here is we have a single cash flow here, 3,472. Okay. And the F that we actually do want to compute is right here. Okay. And so what kind of conversion is this? And so we have a conversion, we have a cash flow that's happening, sometime in the past, and we're converting it to sometime in the future, right? And so this is a very simple P to F conversion. Okay. And so what we have right here is F is equal to, well, here I'm just going to use the compound interest formula. And so here F is equal to P times 1 plus I to the N. Okay. Where this P that we're going to use is going to be the amount that we computed before. Okay. And so we're going to plug in P is equal to 3,472. Okay. I here is 15%, and so it's going to be 0.15. And the N here is going to be 2, because we're moving it 2 years into the future. Okay, and so we plug all that in, and so we have 3,472 multiplied by 1.15 raised to the 2nd power. And what we get is 4,000 $590. Okay. Right, and so this right here, this 4,590, this is the true F that we were looking to compute this whole time. Okay. And so to kind of summarize kind of where we, where this problem went, because I kind of drew a lot here, is that, we had to perform this what I call a non-standard conversion, okay? And we did that in 2 steps. And so we did one step where we kind of condensed all of the uniform series into one lump sum. And then we took that lump sum and then we could transport it at 2 years into the future to get the amount that we wanted, okay? So this is typically what you have to do when you have to do a non-standard conversion, okay? And so non-standard conversions usually mean that you have to perform more than one cash flow conversion to them, okay? Okay. And there's multiple ways that you can do this as well. And so, what way that you end up choosing is kind of up to you, okay? And so, for this particular problem, one way that we could have done this is we could have taken that uniform series and converted to a present sum, and so actually move that back to year 0, get that lump sum there, and then move that lump sum 5 years into the future to that F, okay? And so there's kind of multiple ways that you can approach these problems. And so, if you're kind of working together on the homeworks with your friend, just kind of keep that in mind that there's, you might do it one way different than them. And, most of the time you're going to end up in the same place, okay? But, because of that, there are multiple ways that you can kind of get lost in these kind of problems too. And so my general advice is that, if you are dealing with the problem, if you have a non-standard conversion or non-standard form, I would recommend that you take all of the recurring payments, and so any uniform series arithmetic gradients, and kind of lump that together into either a present sum or a future sum, and because that's a lot easier to move around than the recurring. Okay. Okay. And another point I said earlier, one thing that's really helpful when you're doing these problems is to, really draw out the cash flow diagrams, because when you're doing these non-standard conversions, when you can see them visually, it really helps to keep track of what's going on. Okay. All right. And so on homework 2, that's going to be posted tonight. There's going to be, I think I gave you like 3 problems with non-standard conversions and stuff. I think, that's generally a part that a lot of people, I get a lot of questions on that problem a lot. And so, kind of take it slow. And if you're still kind of having trouble, just, let me know, because I think doing these non-standard conversions is one thing you just kind of have to practice to kind of get used to. All right, any questions on this? Yeah. Oh, of course. Yeah. That's probably the best way to do these ones, because with these problems, because you're doing multiple conversions, it's definitely a lot easier to use the tables, because you're using the formulas to do multiple conversions, then it gets very messy very quick.
So
we say it again. Oh yeah. So actually, we used the tables for this one already. And so, what we did first was we said that, we had this uniform series right here, and we wanted to convert it to, well, in this case, I wanted to lump it together into one sum. And so what I did was I used this conversion. And so this conversion here, I used the tables. And so I basically took the A amount, which was 1,000, and then I converted it to an F. And so I looked into the F over A column for the table with 15% and 3. I looked up that factor in the table, that was 3.472. I multiply that by A, and that's the first F, right? And then what I did from there, and you can use the tables for this one as well, but usually an F and P calculation is pretty straightforward. And so if you wanted to do this with the tables, you would say that F is equal to P times F over P . 15%, and N here is 2. Right? And then you would look up whatever this factor is from the table. Right? I don't have the tables in front of me, so I don't know what that factor is. It looks like it's maybe around 1.2, 1.3, something like that. Kind of just based off those numbers, but that would be how you would do that. No, you multiply by 3,472. Yeah. So actually, you can, and kind of once you get good at these, you can kind of do them in one step. And so you can kind of have multiple conversions in the same calculation thing. And so, for this particular problem, if you wanted to do everything in one step, you can do this, right? And so we started with an A, right? And so that A being 1,000, and we wanted to convert that to an F here. This F here is at year 5. Right? And so the first conversion that we did was we did an F over A, 15%, 3, right? So that was the first conversion that we did in the first step of the problem. Okay. And then since we know it's a non-standard one, we can you can just multiply another conversion factor straight onto that. And so this one's going to be an F over P, 15%. And 2. Okay. And so if you wanted to do, both conversions here into one step, this is how you would do it. Okay. Because this A here, remember, we started with an A of 1,000. Okay. And this factor right here is 3.472. Okay. And so when you multiply these two together, this right here is 3,472. Okay. And then you would multiply that by the F over P factor. Okay. So kind of once you start to get good at these, you can kind of spot the patterns here, and you'll know exactly what conversions you need to apply. And so you'll have kind of multiple conversion factors multiplied together. It's definitely something to practice. And so, I think the first time I saw this, it's like, how did you come up with both of these factors? It's like that, but it's something, once you start to see more, once you practice, it'll become kind of more clear how to do this. Yeah, so that's why homework 2, I think, is pretty critical for these ones, just so you can kind of get the practice for these ones. Okay. All right, any other questions on this? Okay. All right, and so that's non-standard conversions. Okay. And so now let's go ahead and move on to the next topic, which is present worth analysis. Okay. And so present worth analysis is kind of the beginning of kind of like a triple set. Okay. And so present worth analysis is kind of one way to do what I like to call economic comparisons. Okay. And then over the next few weeks, we'll go over different methods on how to perform these economic comparisons as well. But we start with present worth because present worth, I think, is the simplest to do. Okay. Okay, so up to this point, we've gone over all the different types of cash flow that there are and how to convert between them. Okay. And so that's useful if you need to convert between different cash flows, if you want to see how much, if you have a certain amount of money now, how much that's going to be worth in the future at a certain interest rate. Okay. But that by itself isn't super useful for engineering projects. Okay. And so one thing that is useful though is to use what we've learned to perform economic comparisons. Okay. Okay. And so what do I mean by that? So what is an economic comparison? And so, a lot of times as an engineer, you'll be faced with situations where you need to decide, which between, either 2 or 3 different alternatives, which one that you're going to buy. Okay. And a lot of times sometimes it's clear, right? So sometimes it's clear that one way is a lot cheaper than the other ones. But, because of, some complex financing or some complex, way that the maintenance scheduling is, it may not be clear which one is better than the others. Okay. But that's where this kind of comes in. And so using our knowledge of cash flows and how to convert between different cash flows, we can come up with a very kind of clear, systematic way to compare, which are the best economic alternatives in lots of different situations. Okay. Okay. Because remember, the thing that's difficult with engineering budgeting is that a lot of projects take place over long periods of time. And because the value of money is changing over that long period of time, it makes it not 100% clear, what's the best option at times. Okay. And, we're going to do some examples, today and Thursday that, that maybe the results would surprise you, of, what's actually the most efficient way. Okay. All right. So, but before we begin, just like any good engineering problem, we have to talk about our assumptions. Okay. And these assumptions are valid, or these assumptions are going to be made, for all these economic comparison problems. Okay. And so not just present worth, but once we get to annual cash flow and rate of return, we're going to apply these assumptions as well. Okay. 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 And so the first assumption is that we're going to ignore any effects of inflation. Inflation is definitely a hot topic right now with how the world is going. And so I do have a unit on inflation, but we're going to cover that later. And so for now, we're going to assume that basically any prices that we have, maintenance costs, initial costs, everything, those are going to stay the same over long periods of time. Okay. Okay. And the second big assumption that we're going to make is we're going to ignore taxes. So we are going to cover taxes, and so that is something that's important to do. Especially when you're purchasing, big engineering projects. But again, I have a unit on taxes. I think we're gonna spend a couple of weeks on it, but for now, just to keep things simple, we're going to ignore taxes as well. Okay. And that's just mostly just to help keep the math as clean as possible, because otherwise, when you get taxes involved, it starts to be a mess. Okay. All right. Any questions on this so far? Okay. Another important factor that we need to go over. Let me first tell you what present worth analysis is. That might be a good thing to do. Okay. All right. So for present worth analysis, essentially all we're doing is just a cash flow conversion. Okay. And so the idea with present worth analysis is to take, a complex kind of cash flow situation and convert it all into one lump present sum. Okay. And so we're basically converting everything to a P. Okay. All right. So kind of a standard example that you might come across with is, let's say that you're considering the purchase of a piece of equipment. Okay. And so that piece of equipment has its initial cost, it has its maintenance schedule. And so, maybe you have to pay, $150 every month to service the machine. And then once you're done with the machine, you can sell it at the end for a salvage value. Okay. And so you have three different cash flows in one machine. So you have its initial cost, you have its maintenance cost, as well as its salvage. We're going to take all those cash flows and convert it into a single P. And that single P is going to represent, how economically viable or how economically efficient that option is. Okay. You're then going to repeat this for every single option that you have. Okay. And so let's say that you're considering the purchase between machine A, which has a certain cost, certain maintenance, certain salvage, and machine B, which has its own initial cost, maintenance, and salvage. And then, you're going to compare their P values or their present sums, and whichever one is better, that one is the one that you're going to buy. Okay. Okay. And so think of the present sums, or think of the present worth of these options as kind of an economic rating for how well it's going to perform. Okay. And I write best in quotes there because for every problem it's going to be a little bit different, because in some problems we're just going to be considering the cost, right? And so we're going to be considering the maintenance cost and the initial cost. And so the best option there is going to be the one with the least amount of cost. Okay. And so best could mean least cost. Right. And so for problems that only consider that, that's what you're going to consider. Okay. But sometimes, you'll see in problems we're going to be considering revenue as well. And so we'll be able to predict, based on the output of this machine, how much revenue it's going to produce. Okay. And so the best option there might be the one that has the best revenue or make the most money. Okay. Okay, and so we might do some present worth analysis where our p-values are all going to be negative, and so that's all going to represent costs. But we might have some where our p-values are going to be positive too. Okay, but in either case, your goal is the same. You're going to pick the p-value for the option that's the highest. Okay, whether that be the least negative p or the most positive p, doesn't make any difference. It's just whichever p-value is greatest, that's the one that we're going to choose. Okay. All right, and so that in essence, that's all it is. And so it's kind of an application of the cash flow conversions that we've been doing the last 3 lectures. It's just that now we're just doing one extra step where we're just comparing. All right, any questions on this? All right, so before we do an example, one important point I want to make is that when you're doing present worth analysis, the time period of analysis is important. Okay. Okay. Where time period is just basically the end values. Okay. Remember, with present worth analysis, we're going to be doing kind of multiple conversions, right, across multiple different alternatives. And so in order for it to be a fair comparison, the end values for each alternative have to be the same. Okay. And so let me go back to just the simple example of the machines, right? And so if you're going to compare machine A to machine B, right, and you want to do it with present worth analysis, then you have to make sure that they're rated for lasting the same amount of time, right? And so if machine A can only last 4 years before you have to buy a new one, but machine B can last 6 years, in that case, the end values are not going to match up. And so then you have to do something a little bit special to make sure that that you can do a fair comparison. Okay. And so for this first example, we're going to do one where they are matching, and then later on we're going to see what we can do when the end values for our 2 options are different. Okay. But just kind of keep that in mind. And so if you're doing present worth analysis, it's always best if the options have the same length. But if not, there's things that you can do as well. Okay, so with that, let's go ahead and do an example. Let's put some numbers to the example that I've been talking about. All right, so let's say that the engineering firm that you're working for is deciding on purchasing between 2 different machines. Okay. Okay. And the goal with these machines, both machines, they can do the same thing, is that they're going to automate a lot of the processes, a lot of the manufacturing processes within the company to ultimately save the company money. Okay. All right, in this case, both machines have a useful life of 5 years. Okay. And so they're both going to last 5 years before they break. And we're going to assume both machines have no salvage value. And so, after the 5 years, the machine's going to be useless, and then the only thing you can do is just scrap it. Okay. All right, so let's look at our options. And so machine A. Okay. So machine A is going to have an initial cost of $10,000. Okay. And then based on the performance of that machine, it's expected to save the company $3,000 per year. Okay. Machine B. So machine B is going to be a bit more expensive. So machine B is going to cost $13,500. Okay. And so the cost saving for this one is going to be $3,000 in the first year. Okay. And so that's the same as machine A, but every year after that, the cost savings is going to ramp up by $500. Okay. And so we have an additional gradient kind of effect occurring for machine B. Okay. So that means in year 1, machine B is going to save $3,000. Year 2 is going to be $3,500. Year 3 is going to be $4,000, $4,500, so on and so forth. Okay. Okay. And so if we assume an interest rate of 7%, okay, what we want to do is the following. Okay. One, we're going to draw the cash flow diagrams for both options. Okay. Right. So after we draw the cash flow diagrams, we want to determine, which one should we buy? Should we buy machine A or machine B, right? And so on part 2, we're going to use present worth analysis to determine which machine we should buy. Okay. So a lot of writing for this problem, but I want to make sure that we have everything kind of written down. Okay. All right. Any questions? Any questions on the setup for this problem? Everyone's clear on kind of what our goal is going to be for this one. Okay. All right. So let's go ahead and get started with this one. So let's go ahead and draw the cash flow diagrams first. Okay. So let me go ahead and leave this here just so we can see the cash flows. Okay. All right. So let's draw the cash flow diagram for machine A first. Okay. And the wording is a bit different. It's not exactly revenue, but what they used to say, right? I think it's Ben Franklin. A penny saved is a penny earned. And so $3,000 saved is $3,000 earned. And so, whenever you see any problem that says cost savings or it saves cost, you can kind of model that directly as like a revenue. Okay. And so when we draw this cash flow diagram, and so for machine A, we have our initial cost of $10,000. And so let me draw this first arrow here. This is going to be $10,000. Okay. And then every year after that, we're going to save $3,000, right? And so the way that we're going to do this is we're going to put it as an up arrow, right? Insert hat, just like this. Okay. And so that's what our cash flow diagram looks like for machine A. Okay. Our initial costs, and then that's all of our savings after that. So let me see if I can do this without scrolling too far down. Okay, so now let's draw machine B. I might have to scroll down. Okay, so machine B. Now we're going to draw the same line here. Okay, so machine B, we have our initial cost. And so our initial cost for machine B is 13,500. Okay. And then we're going to start to model the cash savings. Okay. Right. And so for machine B, we said that we save $3,000 in year one. And then every year after that, it's going to ramp up by 500. And so year two, we're going to draw a slightly bigger arrow. It's going to be 3,500. Year three, 4,000. Year four, 4,500. And year five, we have $5,000 savings. Okay. And so for machine B, we have a gradient that we need to account for as well. All right, and so those are your two cash flow diagrams. And so these are useful just for visualizing what's going on. And from these cash flow diagrams, you can see that everything is in standard form, right? And so our P's are at year zero, which is great. We have our uniform series. In both problems, we have a uniform series that's going to start at 3,000. Okay, and so that goes from 1 all the way to the end of the period. Okay, so that's good. And for machine B, unique to machine B, we also have the arithmetic gradient. Okay, but our arithmetic gradient here, we don't see an increase until year 2, and so everything here is in standard form. And so this is good, and so we can convert everything here with just single conversions. Okay. Okay. All right. Any questions on this? Okay. All right, so that's part one of the problem. So part one is to draw the cash flow diagrams. Part two is we're going to do present worth analysis. Right. And so for present worth analysis, we're going to take the cash flow diagrams for each machine and then convert it into a single P. Okay. And so, typically, instead of P, I use the term present worth. Okay. And so we're going to compute present worth of A and then present worth of B. We're going to see which one is higher, and then that's the option that we're going to choose. Okay. So, but before we start, it's, hopefully this kind of makes it clear why it's a little bit difficult to choose, which one is more viable, right? Because if you look at this problem, right? Machine A here, has a lower cost, right? And so right from the bat, you're going to save $3,500. Okay. But the amount of cost savings that you're getting every year after that is the same. I guess it would be $3,000. Machine B, you pay a little bit more upfront, and so you pay 35% more, but your cost savings are going to ramp up over time, right? And so the question is, is that ramp up, is that worth it to pay an extra $3,500 at the beginning? Okay. But you can't just add up all these ramps, right? And so I think what's tempting here is to say that you have an extra $500 here, an extra $1,000 here, give an extra $1,500, an extra $2,000. Okay, I'm comparing this to machine A. Okay, and so the tempting thing here is just to add up all of these numbers here and to say that, well, machine B saves us $5,000 over time. Okay, but initially, we pay $3,500 more upfront, right? And so got 5,000 is more than 3,500. And so if we go with machine B, we're saving $1,500 more dollars, right? That's the tempting thing that I think most people will do. But remember, we can't quite do this in this problem because this is taking place over a long period of time, right? Each ticker here is 1 year, and each year that we progress, the value of the money is changing. Okay? And so we need to do this kind of with a proper cash flow conversion. I don't know why I can't say that word today. In order to see which one is better, accounting for the interest rate. Okay. So we can't do this. So let me go ahead and erase this. And so let's go ahead and compute the present worths for both of these options. Okay, so let's start with present worth of A. Okay. And so we're basically going to take all our cash flows here and convert them to a P. Okay. Let's start with the initial cost. And so our initial cost here is $10,000. And so I'm going to do a negative for that because it's a cost. Okay. Okay. And then we need to convert this $10,000 to a P. But, this $10,000 is already something that we're paying at year 0. And so this $10,000 is already in P form. And so we don't actually need to convert this. Okay. And so the initial cost already a P. No conversion. And so that's going to be, and so, and that's part of the reason why present worth analysis is popular, because almost always you're going to have some kind of initial cost. And so under present worth analysis, you don't have to do anything to that. And so you just keep it as it is. Okay. But what we do have here is a cost savings of $3,000. Okay. And this $3,000 here is a uniform series, an A. Okay. And so we need to convert this uniform series to a P. Okay. All right, and so we're going to apply a, I'm going to show you how to do this with the tables, just because it's, I think the work is a lot more clean than if we try to do this with formulas. Okay. And so what we want to compute is a P. Okay. And so remember, the way that you use the tables is that the quantity that you're converting to should be in the numerator. Okay. And what we're converting from should be in the denominator, right? And so the factor that we're looking for here is P over A. Our interest rate here is 7%. Okay. And then our N here, the number of time periods, and so we're going to count the number of arrows that we have. We have 1, 2, 3, 4, 5. Okay. And so our N here is 5. Okay. All right. So here we have a simple arithmetic expression. You're going to look up this quantity here in the compound interest tables. Okay, and so it's going to give you some decimal number. Okay, but I don't have that decimal number in front of me because I only have the final answer. And so if you add in that decimal and then you do negative 10,000 plus 3,000 multiplied by that, then you get a present worth of $2,300.59. Okay. And so that $2,300.59, that is the present worth of machine A. Okay. All right, and so that number there, it's of course it's a number that tells you that it's kind of like a rating of how good this this machine is. But if you take it at its literal definition of a present worth, this machine is something that's going to save you money over the course of 5 years, right? But if you wanted to condense all that money savings into one number, then that's how much money that you would save today. Okay. And so buying this machine, and so one way that people interpret the present worth is that buying machine A is basically the same thing as someone writing you a check for $2,300.59 and giving it to you right there. Okay. It's not quite the same because you have to keep the machine for 5 years in order to get its full value, but that's the equivalent worth, right? And so we talked about it, when you're converting cash flows, you're converting, a cash flow that's equivalent to them. Okay. And so if the company purchased machine A, it would be the equivalent of gaining $2,300.59 today. All right, any questions on this? Okay, so let's do the same thing, but for machine B. Okay, so we're going to do the present worth, machine B. Okay, and we're going to repeat the same analysis. And so, we have our initial cost, and so our initial cost here is $13,500. Okay, we have a uniform series here, and so our uniform series is actually the same as the previous one. Okay, because remember on year one, we have a cost of, we have a benefit of $3,000, and that's something that persists throughout the entire series. Okay, and so that's the same thing as having a uniform series of 3,000. Okay, just like we did for machine A, we're to convert this. Okay, so we have P over A, 7% and 5. Okay. But in addition to that, for machine B, we also have our arithmetic gradient. Okay, because our cost savings is increasing by $500 per period. Okay. And so that increase here is 500, and so that's what we're going to include for that. Okay, and then once again, we're going to use the compound interest tables to convert this number. Okay, and so this 5 here is a G, and we need to convert this to a P. Right, and so we're going to follow the same logic as before, and so our conversion factor that we need is a P over G. Okay, so because we're converting from a G to a P. Okay, our interest rate here is 7%, and our N here is 5. Okay. Remember the standard form for G. So, the amount of time periods where we're actually seeing the increase is 4, right? And so we have 1, 2, 3, 4, right? And so we count the number of times we see increases, then we add 1 to that. So that's why our N for that is 5. Okay. All right. Okay, and so we're going to go ahead and look up those conversion factors. Okay, so this conversion factor here in the compound interest table should be the same as that one. Okay. And then this conversion factor, you can just look it up in the table. You'll have the same table open at 7%. And so if you do the arithmetic here, you add up all the numbers. What you get is a present worth of $2,623.92. Okay. And so based on the present worths of this problem, you know, which machine do you think this company should buy? Machine B, right. And so machine B, you know, the present worth for that one is, you know, worth about $300 more than machine A, right? And so this company were to purchase machine B, you know, the amount of savings that it would get over that 5-year period is equivalent to getting $2,623.92 today. Okay. And so machine B is marginally better than machine A. Okay. And so, you know, what that tells you is that, you know, for this case, it's worth it to pay a little bit more in the beginning to get increased savings over time. Okay. It's not as significant as we thought, right? So remember, you know, when we were doing kind of our naive analysis, you know, we thought that we'd be saving $1,500 more. And so it's not quite that much, you know, but it is better. Okay. And so, you know, what we can see here is that from this analysis that accounts for the interest rates and the time periods, you know, we can say definitively that machine B here is going to save the company more money. Okay. Any questions on this? Okay, so we're almost out of time. And so let's see. Let's just call it here for today. And so, you know, 2 minutes is not enough to talk about anything else. And so we'll go ahead and end it a couple minutes early. And so when we come back on Thursday, you know, we're going to do more examples of this because, you know, I think for these ones, just like everything else, you know, the more examples that you see, the better. And then we're also going to deal with cases for when the time periods are not the same. Okay. So for this one, it worked out because both these machines are going to last for 5 years, but that may not be the case all the time. Okay, so on Thursday we're going to go over how you're going to deal with those situations. Okay, so remember, homework 1 is due tonight at 11:59. If you have it here in person and you want to turn it in, then you can do that right now. But if not, you know, uploading on Canvas is perfectly fine. Okay, and then homework 2 will be up, you know, very soon after homework 1. So have a great afternoon, everyone. Everyone stay cool. It's really hot out there, so stay hydrated, stay inside if you can, and I'll see you guys on Thursday.
Why are we getting interest on our machine?
So that interest rate is a reflection of how much that money is, how much the value of that money is changing over time.
Oh, okay.
Because, you know, and we'll talk about this later. And so, you know, kind of the decision that your company is making is that, you know, if you buy this machine, so, you know, let's say that you have a budget of $13,500, right? And so if you buy machine A, you're going to save $3,500. And so what the company will do then is take that $3,500 and invest it in the market at a 7% interest rate.
Oh, okay.
And so, you know, what you're asking is that, or what the question that we're answering is that, is it better to save some money now, invest it, or use all that money to buy this machine, and which one's going to earn more?
Oh, okay, that makes sense.
Yeah.
Okay. Thank you.
Yeah. Yeah. Yeah.
We're looking for like completion, a grade on completion or a grade on.
So I do, oh, thank you. So I do grade on correctness, but it's only for one problem. So what I do is I choose a problem at random and I grade that one for correctness.
Oh,
But the rest of the homework is graded on completion. So half the points, if you do every single problem, that's half the points automatically. And then the other half of the points are going to be from that one problem that I choose. Random choose.
oh, okay. Am I able to read you even though it's submitted?
Yeah. If you submit, as long as it's before the deadline, you can.
Cool.
Yeah.
Thank you.
Yeah. Zone, is there any final questions? Okay, all right, so I'm gonna go ahead and close up the call. So I'll see you Thursday.